Hello. Today we are performing a comprehensive review of the formulas and proofs underlying ZenoDEX. We will explore how ZenoDEX is not just a single formula, but a carefully curated stack of mathematical claims, ranging from machine-checked theorems to discovery laws. Our objectives include identifying different evidence classes, evaluating proof quality using hardgate and quality dimensions, and reviewing core formulas for constant product market makers, settlement, and routing. Our goal is to understand the curation process that separates expert-level, high-quality proofs from mere machine-generated noise. We will examine each formula's role and the rigor of the evidence backing it. Hardgate of P is defined as the conjunction of 5 rejection gates. The proof builds, contains no placeholders, contains no trust escapes, preserves the intended statement, and has been rebuilt locally. Quality of P is defined as the conjunction of the proof review dimensions used after the hardgates pass. This includes integrity, directness, robustness, auditability, discipline, compositionality, performance, and style fit. In plain English, first ask whether the proof is admissible at all. Only then ask whether it is a good proof. The formulas are the real interface. They show what the system claims, what the proof layer checks, and where the frontier still is. Never ask only whether a proof exists. Ask what kind it is. To begin, we must establish the criteria for what makes a proof admissible, and subsequently, what makes it high quality. In the world of formal verification, simply passing a checker is the floor, not the ceiling. The hard gate of a proof P is defined as the conjunction of 5 essential rejection gates. First, the proof must build. Second, it must contain no placeholders or sorry states. Third, there must be no trust escapes where the logic bypasses the kernel. Fourth, it must actually prove the intended statement without weakening it. Finally, it must be capable of a local rebuild to ensure transparency. Once a proof passes the hard gates, we look at quality. This includes statement integrity and semantic directness. Does the proof show the why, or is it an unreadable mess of machine-generated tactics? We also value robustness against small changes and auditability for human reviewers. In plain English, first we ask if the proof is admissible at all. Only then do we ask if it is a good proof. The hard gates decide whether to reject or quarantine a claim, while the quality dimensions decide if it is S tier, A tier, or merely acceptable. Now, let's look at the overall architecture of the system's claims. We define the shape of ZenoDEX as a multi-layered stack. Shape of ZenoDEX is defined as tau guards and TLA, shadows and lean-proof objects and runtime integer arithmetic and routing objectives and certificates and stablecoin solvency, and oracle safety. In standard terms, the shape of ZenoDEX is the conjunction of the tau guard layer, the temporal shadow layer, the lean-proof object layer, the runtime integer arithmetic layer, and the stablecoin solvency and oracle safety layer, and the stablecoin solvency and oracle safety layer. And the stablecoin solvency. In plain English, ZenoDEX is shaped by several independent kinds of evidence. No single layer carries the whole safety claim. This is a full stack shape summary, not a single theorem. It is important to remember the boundary here. This does not mean every single line of code in the repository is proved. Rather, it defines which layers currently establish the formal shape of the system. Before moving into specific mechanics, we define the conservative release boundary. This ensures that what we claim to be supported is strictly controlled. RC1 claim OK is defined as the conjunction of a clean tree, a frozen scope, green replay lanes, and honest exclusions. In plain English, the release claim is only honest when the tree is clean, the supported surface is explicit, replay passes, and excluded claims stay excluded. This is a release scope contract. It is a conservative public boundary. It is not a claim about every experimental file in the working tree. From a proof review lens, this is a scope proof problem. A reviewer must check that exclusions are explicit and that disputed claims are not silently pulled into the release boundary. Let's move into the mechanics of the constant product market maker. Starting with reserve monotonicity. This is the core requirement that a liquidity pool remains healthy after a trade. The pre-state product, K before, is the product of the reserves before the action. The post-state product, K after, is the product after the action. K monotonic is the predicate asserting that the post-state product is greater than or equal to the pre-state product. In plain English, the pool should not move to a state with a smaller constant product reserve value. This claim is backed by the evidence classes tau contract, implemented, and proved on specific theorem surfaces. However, we must note the boundary. The theorem depends strictly on the admitted arithmetic preconditions and the specific transition law being used. If those preconditions are violated, the monotonicity proof no longer holds. To ensure that the monotonicity we just discussed is actually enforced in the life system, we use the reserve invariant guard. The reserve invariant guard is defined as the conjunction of parameter validity, reserve validity, arithmetic safety validity, drift validity, and constant product monotonicity. In plain English, the guard does not only ask whether k increased, it also checks that the input values are in the domain where the arithmetic reading is valid. This prevents edge cases, where k might appear to increase due to integer overflow or invalid inputs. This is a tau contract evidence class. It represents a boundary. The guard is a contract over a bounded arithmetic surface. It's a vital safety check, but it is not the entire constant product market maker proof by itself. It's the runtime watchman for the math. Now let's examine the actual execution math for a trade. We'll start with exact-in CPMM arithmetic. The fee is the ceiling of input amount times fee basis points divided by 10,000. The net input is the gross input minus that fee. The output amount is the floor of output reserve times net input divided by input reserve plus net input. The new reserves are then obtained by adding the gross input to the input reserve and subtracting the output from the output reserve. In plain English, this is the integer constant product market maker swap rule for exact input trades. This formula belongs to the implemented evidence class. This is runtime arithmetic. While the formula itself is implemented, the proof layer must separately show which invariants, like k monotonicity, this arithmetic preserves. Often, a user knows exactly how much they want to receive. This requires exact-out CPMM arithmetic, which effectively reverses the question. For a requested output, the required net input is the ceiling of input reserve times requested output divided by output reserve minus requested output. The gross input is then the ceiling of net input times 10,000 divided by 10,000 minus fee basis points. In plain English, exact-out asks how much input is needed to receive exactly this much output. This is implemented with a proved sufficient and minimal theorem for the version 8 exact-out surface. The boundary here is feasibility. The request must be possible, meaning the requested output must be less than the available reserve, and the fee denominator must be non-zero. When we say a theorem is high quality, we mean it does more than just work. Let's look at exact-out minimality. The gross exact-out input is computed here by an integer ceiling division identity, written as a floor of the numerator plus denominator, minus 1, all divided by the denominator. In plain English, this integer expression is not an approximation, it is the exact integer way to compute the mathematical ceiling. This is proved for the version 8 exact-out sufficient and minimal theorem. From a proof review lens, this is a high-quality theorem shape because it proves both sufficiency, that this amount works, and minimality, that no smaller integer would work. A weaker proof that only showed this input works would not establish the canonical behavior we need for a deterministic exchange. To handle very large trades, we use fee ceiling decomposition. This avoids large numbers causing errors in the calculation. The fee on a gross amount G at fee rate F is the ceiling of G times F divided by 10,000. It decomposes into the fee contribution from the quotient part of G divided by 10,000 plus the fee on the remainder. In plain English, large fee calculations can be split into a safe large part and a small remainder part without changing the result. This is a proved arithmetic theorem. From a proof review lens, this is a reusable arithmetic lemma. Reusable lemmas improve overall proof quality, because later swap proofs can call this lemma instead of repeating low-level ceiling arithmetic. This leads to cleaner, more maintainable, and ultimately more trusted proofs. Beyond individual swaps, we need a way to talk about the movement of value across the entire system. We call this settlement algebra. A settlement is an integer pair representing changes in two tokens. Settlement composition, using the circles operator, simply adds the first coordinates and adds the second coordinates. The identity is the zero pair, and the inverse of a settlement negates both coordinates. In plain English, executed value movement can be summarized as a signed two-token delta, and these summaries composed simply by addition. This is a proved property. The boundary to keep in mind is that this describes the algebra of the settlement summary. the final result, not the full runtime execution path that produced it. It is a high-level abstraction for reasoning about net results. Building on that algebra, we introduced the net flow homomorphism, which helps us track the total value entering or leaving a set of trades. The function delta maps a settlement to the sum of its two signed coordinates. Applying delta after settlement composition is equal to adding the delta values of the two individual settlements. Balanced settlements are defined as the kernel of delta, where the sum is 0. In plain English, the net flow score respects composition. If two settlement summaries are combined, then net flow scores add up linearly. This is proved. However, the boundary here is usefulness. The value of delta as a metric depends entirely on whether this specific net flow abstraction matches the economic question you are trying to answer. It is a tool, and you must use the right tool for the job. Now let's bridge our CPMM, trade math, with this settlement algebra. This is where we see how individual trades fit into the larger system. A CPMM swap with input A and output B maps to the settlement pair A-B. Its net flow value is a minus B. Composing two such settlement images is equivalent to the settlement image of the summed inputs and summed outputs. In plain English, the CPMM swap can be embedded into the settlement algebra without losing its additive structure. This is a proved property, acting as a bridge between a swap summary and settlement algebra. From a proof review lens, this is a prime example of compositional proof quality. This theorem creates an interface between CPMM arithmetic and the more general settlement algebra, allowing later proofs to reason about settlements without needing to reopen the entire swap implementation every time. Why does the constant product k never decrease in an ideal, zero-fee integer system? We can prove it through the zero-fee k-gap law. The zero-fee output is the floor of y times a divided by x plus a. The post-swap product equals the pre-swap product plus the Euclidean remainder of y times a, modulo x plus a. Therefore, the post-swap product is always at least the pre-swap product. In plain English, the integer rounding dust is exactly why the zero-fee integer CPMM does not decrease k. This is a proved zero-fee theorem. From a proof review lens, this exact remainder identity is much stronger than a simple black box inequality proof. It explains why the inequality is true, which makes the proof more auditable, easier to reuse, and ultimately higher quality. Moving on to batch auctions, we need to define what makes a trade valid when it's part of a group. This is batch outcome typing. An intent contains an input amount and a minimum output. A valid outcome is either unfilled or filled with an output value. O, equipped with a proof that the output is at least the intent's minimum output. Surplus is therefore non-negative for every valid outcome. In plain English, the type of a filled batch outcome carries the minimum output condition with it. You can't have a filled outcome without also having proof it met the user's limit. This is proved. The boundary here is that it proves validity after a candidate outcome is represented in the typed surface. It doesn't tell us how to choose the best batch, only that the one we chose is valid. So how do we define best? We use the batch objective, which measures volume and surplus. The volume of an unfilled outcome is 0, and for a filled outcome, it is the input amount. The surplus of an unfilled outcome is 0, and for a filled outcome, it is the actual output minus the minimum requested output. The AB objective then pairs these two values, volume and surplus. In plain English, the batch objective first records how much trade volume was filled, and then how much extra surplus those fills created for the users. This is a proved property. It's important to remember the boundary. The objective is only as meaningful as the ordering and tie-breaking policies you select to use with it. It provides the metric, but not the final decision rule by itself. Each filled pair in a batch maps to its corresponding CPMM settlement, and each unfilled pair maps to 0. A batch settlement is the left fold of settlement composition over those pair settlements. The settlement of an appended batch is then equal to the composition of the settlements of each individual part. In plain English, batch settlement is compositional. If you split a batch list and fold each side, you get the same settlement summary as if you folded the combined list. This is a proved property concerning the fold and settlement abstraction. However, it's a boundary to keep in mind. This doesn't make every batch candidate feasible. It only tells us how to represent them once they are. Now, how do we choose the single winner from many possible valid batches? we use the canonical batch winner rule. The canonical key orders volume and surplus in the opposite direction, effectively maximizing them, and then orders by the usual lexicographic direction for tie-breaking. For every finite, non-empty set of keys, there exists a unique key that is the minimum. In plain English, this rule turns maximize volume, then maximize surplus, then choose a deterministic order into a single unique minimum key theorem. This is a proved property. The boundary is that this proves uniqueness over a fixed candidate set. Generating those candidates is a separate obligation. From a proof review lens, we must ask if the proof exposes the underlying ordering invariant or just case splits through the definition. Our current heuristic scan marked this as acceptable, but in need of curation to improve its style and readability. For routing across multiple pools, we have a similar logic: the exact out route key. The exact out route key is a triple of total input, leg count, and a lexicographic leg list. Every finite non-empty set of such keys has a unique minimum. At equal input, the minimum has no more legs than any competitor. At equal input and leg count, it has a lexicographic smaller leg list. In plain English, for exact out routes, the canonical route minimizes input first, then uses fewer legs, then chooses a deterministic order. This is proved. From a proof review lens, we must distinguish between finding a unique minimum over omitted candidates versus a complete search over all feasible candidates. The formula is only as strong as the candidate set statement it relies on. This leads us to the exact out runtime checker. This is a crucial component that ensures the router's choice is actually the best one. In standard reading, if the packet is valid, quote totality holds, and the path witness stream covers the guarded input surface, then there exists a feasible allocation whose canonical candidate is the runtime choice, and that choice is the best one possible according to the key. In plain English, the checker theorem separates solving from checking. A generator can be as complicated as it needs to be, but as long as it provides the right witness stream, the checker can prove the chosen route is canonical. This is a proved property, but it's conditional on witness coverage. From a proof review lens, this is a great teaching point. The theorem is strong, but a reviewer must never erase that coverage condition when explaining why the result is correct. To prevent replay attacks and ensure transaction order, we use a non-cess temporal model. The next state relation is the disjunction of accept, stale rejection, and gap rejection. An accept transition happens for a nonce n that is exactly 1 greater than the last used nonce. It then records the requested nonce, updates the history, and sets the accepted flag to true. In plain English, the nonce shadow model only advances on the next sequential nonce. It's a simple moving frontier. This is a TLA shadow evidence class with a related lean no replay theorem. The boundary is that the TLA layer uses bounded model checking unless it has been separately promoted to a full unbounded proof. Following that, we have the theorem for no replay in later valid sequence, which ensures that once a nonce is used, it can't be used again. The last nonce, after a batch of length m, is just last plus m. Every nonce in that first batch is strictly less than the first nonce expected in the next batch. Therefore, a later valid sequential batch cannot replay a nonce from the first one. In plain English, sequential nonce batches create a moving frontier. Once that frontier moves, old nonces are left behind forever. This is a proved property. The boundary here is that it's a theorem about the model's sequential nonce surface. It's not a claim about every possible network-level replay condition. From a proof review lens, the main risk isn't the math, but rather any semantic mismatch between these model batches and the actual deployed replay boundary. Before a transaction can even be considered, it must pass the transaction envelope validity check. Requested envelope validity is the conjunction of 3 core parts: paired required arguments, valid bounds, and a valid stream scope. In plain English, a transaction request is only valid when the required fields are paired, their bounds are valid, and the request uses the allowed stream surface. This is a TLA shadow evidence class. The boundary here is that this is an admission model. It does not prove that downstream settlement is correct, only that the request itself is formed properly for consideration. It is the door guard for the system. When we talk about stablecoin solvency, we need to ensure every vault is healthy. This is the ZUSD minimum collateral ratio, or MCR. The MCR predicate holds when debt is zero when the collateral value clears the required threshold. MCR headroom is simply the left side minus the right side of that inequality. In plain English, the vault is safe when collateral value is high enough to cover the debt, plus the required buffer. Headroom measures just how far above or below that threshold a vault is. This is an implemented evidence class, with lean arithmetic support for those headroom formulas. The boundary here is vital. The inequality is only as good as the oracle price and the unit's discipline used in the calculation. It's safe math, but only if the inputs are trustworthy. To protect the system during volatility, we have the ZUSD risky operation gate. This stops users from making certain moves if the oracle is unreliable. Oracle freshness requires that an oracle has been seen. The staleness bound is non-negative, and the time since the last update is within that bound. Risky operations are then allowed only when the oracle is seen. Prices are positive and synchronized. The oracle is fresh, and the system is not in recovery mode. In plain English, risky operations are blocked unless the oracle is present, fresh, positive, synchronized, and the system is outside of recovery mode. This is an implemented property. Keep in mind the boundary. The gate is a runtime predicate. It doesn't prove that the oracle itself is telling the truth, only that it is behaving according to these specific rules. To maintain the core logic of the stablecoin, we enforce several stablecoin runtime invariants. In standard terms, if the oracle is seen, prices must be positive. If the oracle is seen, the pending price must be at most the current price. If the oracle hasn't been seen, all price data must be zero. Finally, free debt plus stability pool debt must always equal the total debt. In plain English, the runtime keeps the oracle state and the debt accounting in a very tightly constrained shape. This is implemented. However, the boundary is that these are state invariants checked by the implementation surface. They are not a complete economic proof of stablecoin safety. They just ensure the bookkeeping is internally consistent. In perpetual markets, we have the perpetual collateral clamp safety rule to prevent sudden massive price swings from breaking the system. The allowed move delta is MP divided by 10,000. The clamped price is the raw price clipped into an interval from P minus delta to P plus delta. The absolute difference between the clamped and old price is therefore at most delta. In plain English, any single oracle update is forced to stay inside a bounded price move envelope. This is a proved property. The boundary here is that the collateral non-negativity theorem depends on this bounded move assumption and a maintenance margin condition. From a proof review lens, this is where assumption hygiene matters. A proof can be excellent mathematically, while the overall system claim is still conditional on these bounds being correctly enforced by the environment. Just as we guard the reserves in CPMM, we also have a perpetual exposure guard to ensure accounts don't over-leverage. Exposure safety is defined as the conjunction of net exposure validity and gross exposure validity. In plain English, an account has to pass both the net and gross exposure checks to be considered safe. This is a Tau contract evidence class. The boundary here is that this is a guard formula, not a full liquidation or funding theorem by itself. It's the check that must pass before any further action is allowed. To maintain balance between long and short positions, we use funding balance, which ensures that what one side pays, the other side receives. Symmetric funding returns a pair, where the first component is the funding payment and the second is its negative. Its net flow value is zero. In plain English, in the rational arithmetic model, one side's funding credit is exactly the other side's debit. This is a proved property of the funding algebra, with a separate status on older settlement claims. The boundary here is that integer rounding and authorization require separate evidence. From a proof review lens, a proof of balanced arithmetic is not automatically a proof of authorized settlement. This is a key distinction that a curator must preserve. For token actions like minting or burning, we use the protocol token one-hot policy. This ensures that only one of these actions can happen at a time. The one-hot 3 predicate holds when exactly one of transfer, mint, or burn is active. The policy is okay when underflows are avoided. The one-hot rule is followed, and the active action passes its own specific validity rule. In plain English, only one token action is allowed at a time, and that action must follow its own rules. This is a Tau contract. The boundary is that this is an action shape policy. It ensures the mechanics are right, but it doesn't prove whether the tokenomics behind them are desirable or not. When routing between two pools, we use two-pool exact-in routing to find the best split of a trade. The best exact-in split for a total input D is the allocation A that maximizes the sum of the outputs from both pools over all integer allocations from 0 through D. In plain English, the router searches for the split of one input amount across two pools that gives the largest possible total output. This is implemented with additional proof surfaces for routing certificates. The boundary here is that the objective simply states what is being optimized. Separate proof is still needed for any shortcuts that claim to avoid scanning every possible split. For exact-out trades, we have the two-pool exact-out routing rule, which asks how to split a desired output while paying the least input. The best exact-out split for requested output Q is the allocation Q0 that minimizes the total input, where pool 0 provides Q0 and pool 1 provides the remainder. The feasible interval is bounded by the available reserves in each pool. In plain English, the router asks how to split a desired output across pools while paying the least amount of input possible. This is an implement property. The boundary here is that this exact-out canonical theorem is over the emitted candidate surface, unless a stronger generator completeness proof is supplied separately. To speed up routing, we use a k-pool continuous split as a relaxation of the problem. Each pool's continuous output function is g of I. The total continuous objective is the sum of those per pool outputs, subject to a total allocation D. Since the second derivative is negative, the function is concave. In plain English, the continuous version of the problem is concave, so equalizing marginal output is the natural starting point for finding the best integer split. This belongs to the tested discovery evidence class. The boundary here is that continuous concavity does not automatically prove integer optimality for the runtime system. From a proof review lens, this is discovery evidence, not final proof. A curator must ask whether this continuous theorem has been properly bridged to the integer runtime. Using that continuous version, we can find an equal marginal routing seed to give the solver a head start. At the continuous optimum, every active pool has a marginal output equal to a common multiplier, lambda. Solving that equation gives a formula for the optimal allocation, AI star. We then check a small integer envelope around this point. In plain English, the continuous solution tells the integer solver exactly where to look. This is a tested discovery claim. The boundary is that this finite neighborhood is only a candidate surface unless a theorem proves it covers all possible integer optima for the exact runtime domain. From a proof review lens, the question is coverage. Does this envelope actually contain every optimizer, or is it just a very good heuristic? To ensure the search is efficient, we use the DTSSR evaluation bound, which limits the number of steps the solver needs to take. The near unimodality bound states that for 3 ordered points, the middle value plus 2 is at least the minimum of the outer 2. This property allows us to bound the number of ternary search steps needed to reach the solution. The total evaluation budget is at most logarithmic in terms of the input D. In plain English, the split search can be bounded logarithmically under this proved near unimodality surface. This is a proved property. However, it is strictly tied to the modeled split objective and any approximation assumptions that were made. It guarantees efficiency, but only within those specific bounds. One interesting mathematical property of CPMMs is anti-fragmentation. It is better to do one big trade than many small ones. The anti-fragmentation law states that executing a combined input all at once returns at least as much as executing the pieces sequentially in the same direction on the same pool. The fragmentation gap is this difference, and it is always non-negative. In plain English, for trades in the same pool and direction, splitting can lose you output, but it can never create free output. The zero-fee version of this is proved, while the fee-aware version is currently a tested discovery claim. From a proof review lens, this is why evidence tags matter. These two formulas look similar on screen, but they have very different levels of formal proof strength behind them. Sometimes the order of trades matters, which we measure using settlement ordering sensitivity. The commutativity gap is the absolute difference in total output between two different execution orders. The commutativity norm is the maximum possible output over all orderings, minus the minimum possible output. In plain English, some settlement sequences are sensitive to the order in which they happen. This formula measures exactly how much that order matters. This belongs to the tested discovery evidence class. The boundary here is that this is a diagnostic quantity. It's not a blanket proof that all orders are safe or unsafe, but rather a tool to find potential risks. From a proof review lens, these diagnostic formulas are useful search instruments, even when they aren't full theorems. Finally, we must be honest about where the math is still being debated. These are the disputed derivative claims. In standard terms, the current disputed set includes the funding rate market authorization claim and the curve selection market authorization claim. In plain English, these specific claims are currently held outside of the stronger public authorization boundary. This is the disputed evidence class. The boundary here is specific. Older versions of these claims relied on environment-supplied values that are now under review. From a proof review lens, disputed doesn't mean useless. It just means the stronger claim is not yet accepted. A good curator preserves the useful parts of these sublemmas while refusing to overstate the validity of the broader claim. We conclude our review with the closing formula, which represents the complete evidentiary state of the project. ZenoDEX evidence is defined as the conjunction of mechanism formulas, boundary formulas, certificate formulas, and exclusion formulas. In plain English, the strongest reading of this project is not simply that everything is proved. Rather, the strongest reading is that the project has a precise map of what is proved, what is implemented, what is checked, what is discovered, and what is excluded. The formulas are the real interface. They show exactly what the system claims, what the proof layer checks, and where the research frontier still is. As we've seen, the difference between an expert curation and a generic machine proof lies in this transparency and structural integrity. The final review habit is simple. Never ask only whether a proof exists. Ask how good that proof is, what assumptions it hides, and whether it truly exposes the invariants that make the system safe. Thank you for joining this deep dive into the mathematical stack of ZenoDEX.